Well, hello everyone. We are in time, so some of our colleagues are still taking breakfast, so they are going to join us soon. But because today we have a tough schedule, we need to be done at 12, if I recall it more or less well. We need to be in time, so we are going to start right now with what we call the KPRK talk. A KPRK is the English meaning for Caparica, KPRK, okay, talk. And we normally, we decided to start this kind of talks 1 year ago. And the idea is to bring people who is developing something really new or something really outstanding in research. We record this talk and we made this talk available through YouTube and through our webpage. So you can come again and recall it at any time. And it is my great pleasure to introduce you today. Oh, I need my glasses. So, it is my great pleasure to introduce you today Professor Bin Hu, that comes from the Laboratory of Analytical Chemistry for Biology and Medicine, from the Department of Chemistry, from the Wuhan University in Wuhan, China. And the organizing committee found really outstanding his research regarding chip-based sample treatment, in which he can even do trace analysis in cells. And so I thank you, Professor Bin Hu, for accepting to be here today giving this Caparica talk. Thank you.
Thank you. Good morning, everyone. First of all, I would like to take this opportunity to thank Professor Capella to have me here, and also for his kind introduction. Today, I will talk about chip-based sample pretreatment techniques for trace matter analysis and their species analysis in cells. As we all know, trace matter play a very important role in life system, while cells is the basic unit for the life. Therefore, trace matter and their species analysis in cells has become one of the most important research topics in modern analytical science. However, due to the cell's heterogeneity, how-to determination of trace matter and their species in small number of cells, and even single cells is a big challenge, because the cell sample volume is very, very small, sometimes even single cells. And also the target analyzed at the very low, extremely low concentration in the cells. And also, sometimes the matrix of the cells is very complicated. Therefore, the development of miniaturized, high selective, and high sensitive analytical platform for trace matter and their species analysis in cells is highly demanded. Fortunately, Microfluidic chip, which was appeared in last 90s, is a highly integrated cells manipulation platform. So it occurs to us, if we integrate the sample preparation onto a microfluidic chip and combine it with cells manipulation in one microfluidic chips, maybe we can develop cells analysis with ICP-MS as a subsequent detection techniques. Because as we all know, ICP-MS is one of the most powerful analytical techniques for trace matter analysis due to its high sensitivity. If we combine microfluidic chip-based sample preparation with ICP-MS, first we should consider how to combine these two systems. Therefore, we should develop micro-amount sample introduction techniques for ICP-MS. In this case, in our research group, we have so many years experience with electrothermal vaporization, micro amount sample introduction techniques for ICP OES and also ICP-MS, because normally it consumes microliter volume for the liquid sample and with very high sensitivity. Also, if you would like to get the species information, we should combine it with HPLC-ICP-MS. In this case, capillary HPLC-ICP-MS combined with ICP-MS won't be a suitable choice. In our research group, we have some experience on micro-extraction techniques, such as liquid phase microextraction, magnetic solid phase extraction, and also monolithic capillary microextraction. So if we integrate this kind of microextraction technique and combine it with cells manipulation into one microfluidic chip, we can develop different kind of methods for trace matter and their species analysis in cells. In this case, this is a typical chip-based liquid phase microextraction. As you can see, we can base the laminar flow and the target analyze diffuse from the aqueous phase into the organic phase. And then we connect the organic phase for subsequent ET-phase ICP-MS determination. And we also can integrate magnetic solid phase microextraction, into the microfluidic chips and try to develop chip-based magnetic solid phase microextraction. And similarly, we can also integrate the monolithic capillary microextraction into the microfluidic chip and combine it with the cells manipulation, develop chip-based monolithic capillary microextraction with ET-phase ICP-MS for cells analysis. As you can see, with this kind of miniaturized sample preparation, we can get the cells consumption number from the conventionally millions of cells to 50,000 of cells for chip-based liquid microextraction to 5,000 Hep2 cells for the chip-based magnetic solid phase extraction, or even 800 yeast cells for chip-based magnetic solid phase extraction, and even 600 Hep2 cells for chip-based monolithic capillary microextraction. If for this kind of chip-based sample preparation, we use the ET-phase ICP-MS as the subsequent detection techniques. And this one is an offline detection technique. So if you would like to development an online system, we should take consideration of the sample throughput. In this case, we try to fabricate the chip-based aerial microextraction for online combined with ICP-MS. This is typical chip-based aerial monolithic microextraction device. As you can see, the yellow one is the 6 parallel capillaries. And we also used the V1 to V10 as microwaves to control the extraction process. And also we have I1 and I10 as the inlet for sample introduction and also elution solution. And we have another 6 outlet for connection, the elution solution, and also the sample effluent. During the extraction, we get the sample getting through the 6 capillary parallel. And then through the microwave, we control. We first get the first capillary elution solution through, and then online subsequent determination by ICP-MS. And the rest of 5 is kept off. After that, we switch on the second column and switch off the first column to perform the similar elution also for the subsequent determination. And this is a typical controlling program for microwaves. With this kind of system, we can get very good detection limits at from the 12 to 23 nanogram per milliliter. We also can use the development method for the analysis of trace mercury, lead, and bismuth in HepG2 cells and human urine. Similarly, we can develop an online system, chip-based magnetic solid phase microextraction with HPLC-ICP-MS for animal speciation in cells. In this case, we use the sulfolated polyester-coated magnetic particle as the adsorbent for magnetic solid phase extraction. This is the typical chip-based microextraction device. We use this kind of device try to extract the selenium, different kind of selenium amino acid. And this is a typical extraction at HPLC conditions. And here I will show you the column packing process. As you can see, we can get well homogeneous magnetic particle packed in the central extraction channel. And this is the packed column before dried, after dried, and after used. As you can see, 3 of them looks almost the same, which means this kind of packed column could be repeatedly used. During the extraction process, we first get the magnetic nanoparticle self-assembled in the central channel of microfluidic chips, and then we get the cells suspension and also the self-rupture solution and mixed in the mixed zone on the microfluidic chips. After the cells rupture, and the rupture solution was get through the central channel of extraction to perform the solid phase extraction. After that, we use the elution solution to get the retained target analytes through the outlet, and then connect them for subsequent online combined with HPLC-ICP-MS for the subsequent selenium speciation. This is a typical analytical performance for this kind of a combination, and also the real sample analysis chromatogram. In this case, we just confirm the cells number of 800 yeast cells. Similarly, we can develop a chip-based area magnetic solid phase microextraction online combined with capillary HPLC-ICP-MS for mercury speciation. This is a typical diagram for this combination system. This is a typical chromatogram we obtained with the HepG2 cells incubated with inorganic mercury and mass mercury. As you can see, for mass mercury incubated HepG2 cells, we can get 2 species. One is mass mercury. The another one is mercury, inorganic mercury, which means there's demethylation of HepG2 cells, mass mercury in HepG2 cells. This is a typical analytical performance for this hyphenation system. We use the development method for the speciation of the mass mercury in HepG2 cells. And we also use because we find that the mercury and the mass mercury incubated HepG2 cells have different kind of species. So we use sex exclusion chromatography combined with ICP-MS for the fractionation of different kind of concentration of inorganic mercury and the mass mercury. As you can see, for the inorganic mercury, the peak 3 and the peak 4 changed remarkably. But for mass mercury, peak 1 and the peak 4 their OP-fields change. In this case, we have two analytical techniques. One is for cylinder speciation, and another one is for mass mercury speciation. So it occurs to us, if we use these two established methods, maybe we can study the cylinder mercury antagonism with the HepG2 cells as the model cells. As we all know, this kind of antagonism is a very typical in inorganic, bioinorganic chemistry. In this case, we first tested the MTT assay. As you can see, cylinder system provide the most OP-fields cylinder mercury antagonism in HepG2 cells. Our ETV-ICP-MS results also confirm these facts. So we try to develop this kind of workflow for the study the antagonism of cylinder system to mass mercury. First, we use ETV-ICP-MS for the total mercury and the total cylinder determination, and then we use the ultrasonication centrifugation to get the supplement for chip-based HPLC-ICP-MS speciation, and also size exclusion chromatography ICP-MS for the fraction, and also the after ultrafiltration, we use the reversed phase HPLC-ICP-MS for speciation. And this is typical analytical results for SEC-ICP-MS, and also reverse the phase HPLC-ICP-MS for the cells rupture solution. As you can see, the peak 6 and the peak 7 changed very obviously with the incubation time and also the cylinder system to the mass mercury ratio. Similarly, you can see the peak of mass mercury and the GSH and also mass mercury system changed very obviously with the incubation time and also the ratio of cylinder system to the mass mercury. And then we use the reversed phase HPLC-ICP-MS for the speciation of mercury in the culture media. As you can see, the concentration of aggregation of mass mercury and the cylinder system in culture media decreased along with the increase of the incubation time, as you can see from the B to figure B to figure D, demonstrating that the aggregation of mass mercury and the cylinder system is the main species to promote the cell's uptake mass mercury. And then only the mass mercury GSH and the mass mercury system were found in the fresh culture media, and their concentration increased with the increase of elimination time, indicating that mass mercury GSS is the main species for cells elimination of mass mercury. This is the new findings from the cells with the HepG2 cells as a model to study the cylinder mass mercury and the mercury antagonism. In this case, we find a new species, mass mercury and the aggregation mass mercury and the cylinder system. And then we use the mercury and the cylinder as the target analyte to get the chromatograph like this. And we found the stoichiometry of mass mercury to the cylinder system is 4:1 in the peak. In this case, we try to use the nuclear magnetic resonance and also the high resolution mass spectrometry, try to identify or try to elucidate what is the interaction force between these two species. Unfortunately, we cannot get any proof to elucidate the interaction between these two species. And then we try to use the chemical calculation, and it was found mass mercury interact with selenium cysteine to form mass mercury and selenium cysteine aggregation due to a very weak interaction between these two species. As we talked previously, the chip-based laminar LPME could be used for ET5-ICP-MS analysis of trace metals in cells. But this kind of combination system, the extraction efficiency is not very high. So in this case, we try to fabricate microfluidic droplet-based liquid phase microextraction and try to combine it with ET5-ICP-MS for cells analysis. In this case, three functional paths were designed. The first one is droplet generation, like this. And the second one, extraction zoom. And the third one is phase separation. For the droplet generation, we designed a cross like this, and which is referred as the flow focusing geometry, and also the channel leveled down in the focusing part for generating stable organic drop, macro drop. In the extraction zone, separating channel were designed for better extraction performance, and the total length of the extraction channel is 185 centimeter. Of course, we use the orthogonal experiment design to optimize the width and the length of the different channel. And then we design this kind of phase separation. I think this one is the most important for this kind of microfluidic chips. And we use the hole punch, get a hole at the hole A position, and then get the stainless steel bar plugged into this hole. And we try to optimize the position of the end of the bar and the channel of and also the outlet channel. For PDMS microfluidic chips, we want also, if you want to get the very stable oil invert system, we should get the PDMS surface modified hydrophilic modification. So in this case, we use the PDA combined with BSA to hydrophilic modify the PDMS, which indicate that this kind of modification is very successful for the getting a better stabilized micro droplet. And then we try to study the effect of position stainless steel bar in the hole A. As you can see, in this case, we can get very good laminar flow, both organic phase and also aqueous phase. And then we use SEM to determine the distance of, and found the distance is like indicated here. We also use the determination of the contact angle of the micro drop on the stainless steel. As you can see, the contact angle is 61 degrees. Why this kind of phase separation could be successful, get the phase separation? We would like to conform it theoretically. So in this case, we use a theoretical model, try to stimulate the phase separation process. This is relevant parameters in theoretical model, and also the line flow, outlet line flow of the organic phase and also the aqueous phase. And then we use the Comsol multiphysics version 5.3, try to stimulate the phase separation process. This is the typical phase separation process. As you can see, with the process at here, you can get the laminar flow of the organic phase and also aqueous phase. In this case, we just get the contact angle is 30 degrees, which is half of 61 than previously we detected. Okay. Here. So what's the problem with that? So in this case, we referred to the Windsor principle. There's rough contour. So in this case, the theoretically surface of the end of stainless steel bar, and also the surface normally is rough. So there's actual surface of the stainless steel bar and also the geometric surface. And this ratio is the rough contour. After SEM characterization of this gamma rough contour, we find that the rough contour is 1.6. And then based on the Windsor principle, we can get the contact angle of stainless steel bar is less than 35 degrees, which coincided with the 30 degrees, which demonstrate this kind of phase separation is very successful. And then we use the oscilloscope experiment to optimize the extraction parameters, and then evaluate the DDTC both as a chemical modifier for subsequent ETV-ICP-MS, which demonstrate DDTC could be a very excellent chemical modifier for subsequent ETV-ICP-MS determination. And this is a typical analytical performance, and also the coexistent ions interference, and also the analytical performance and the real sample analysis for halo cells and the hepatitis cells. The last, I will show you a Facile droplet chip online combined with time-resolved ICP-MS for single-cell analysis. In this case, we also develop close-like microfluidic chip, and then online combined with time-resolved ICP-MS for single-cell analysis. One should keep in mind, if you should combine these two systems, the first you should choose the suitable fluids for the droplet, because the organic phase should be compatible with ICP touch. And the second, the droplet microfluidic device should keep the 100% of the droplet encapsulating for the single cell. And the third one, the interface between microfluidic chip and also the ICP-MS should keep the suspension stability of droplet, and also including the baseline of ICP-MS and the time-resolved development time and something like that. And first, we choose the suitable fluids on the droplet chip. Normally, for droplet chip, the large number of carbon organic solvent were used. In this case, it's not suitable for ICP-MS detection. So we try to find a suitable organic solvent with low number of carbon. So in this case, we found HC alcohol with 1% span 18 at flow rate of 12.5 as organic phase. We can get very good stable of micro droplet. And also the aqueous phase is 1% hydropropyl cellulose in PBS. And this is the fluids for the droplet chip. And also we try to develop the an interface for microfluidic chip and also for the ICP-MS. And then we try to optimize the droplet microfluidic device parameters, such as the different channels, lengths, widths, and the focus channels, widths, and something like that. And then we found the width of flow focusing channel is 75 micrometer. And also the length of droplet generation channel is 3 milliliter. We can get very good, stable droplet, organic droplet. We also try to optimize the interface and also the flow rate of organic phase and also the aqueous phase. As you can see, the interface is fused silica capillary with 3 centimeter long and 75 micrometer inner diameter. And also the aqueous flow rate is 5 microliter per minute. And also the 2 organic phase is 12.5 microliter per milliliter. And then we optimize the cell's density, try to get the single cell encapsulation. And in this case, we find the cell's density like this. We can get the 1%, 100% of the single cell encapsulation. And in this case, the probability of droplets contained 2 cells is lower than 3.4 times 10 to minus 5%. And then we try to optimize the divider time for single cell detection, and then we get the pump peak, and then through the mathematical transfer into the figures like this, and then we use the 222 nanogram zinc oxide nanoparticle as a calibration standard. We can get the single cell's zinc content is 21.7 femtogram per cell. And then we use the conventional ICP-MS for the acid digestion, large number of cells, and try to get the single cell's content. And it's 25 femtogram, which both of them coincided very well. Now let's come to, and this, we use the development method, try to investigate the HAPG2 cells uptake zinc oxide nanoparticle. You can see the cells without zinc oxide nanoparticle, with 1, with 2, with 3. It's quite easily use this kind of method to investigate the cells uptake the nanoparticles. Now let's come to the conclusion. By integrating different kind of micro-extraction techniques into the microfluidic chips, we can develop different kind of strategies by combining this device with ETV ICP-MS, microflow labilization ICP-MS, and also capillary HPLC-ICP-MS for trace matter and their species analysis in cells with very high sensitivity and also the cells consumption number could be reduced from conventionally millions to as low as 600 cells. And also a single cell encapsulation was realized on a Facile droplet chip with high throughput, and an online droplet chip ICP-MS single cell analysis system is developed. And this system could be used for the single cell uptake nanoparticle. Future research will be focused on the further decrease of the consumed cell numbers, single cell analysis, and the cytotoxicity study of nanoparticles containing metals. So many thanks for different kind of funding agency for their financial support for our research work, and all our graduate students and our colleagues in my atomic spectroscopy and mass spectroscopy research group at Wuhan University, and all of my collaborators. Thank you all for your attention.
Thank you. Thank you very much. Thank you indeed. Outstanding presentation. We have time for questions, and I would like to be the first in asking. Yeah, your turn will come soon. You are focusing these devices in methyl and methyl speciation, so I have two questions. The first one is something more general. Are you trying to apply this to proteomics to study the changes in protein content of cells, proteins, and proteomics? Are you trying to apply this to these studies?
Good question. At present, we really use this kind of device for metallomic study, especially for such as I talked about. We use this kind of device for the study selenium, mercury, and goldison. I think this is really kind of metallomics. And also we use this kind of techniques at present. This kind of work is undergoing to study the cell's uptake, the nanoparticle, and try to study the nanoparticle metabolism in cells.
Because, well, because this is a brilliant way to find out in real time how a cell reacts over the presence, let's say, of mercury. But what it could be really interesting also is to check the change in the proteins, which is associated to this change in methyl and methyl speciation, because through the proteins, you can go to the genes, and then you can check out exactly how the genotype is responding to the contamination. So we can talk later about this, because I think this can be a good project.
Okay, no problem, yeah.
And the second one is more specific. From an analytical point of view, my concern, when I work with some metals like zinc or other very common metals, is contamination. So the point is, you are using ICP-MS, which is a technique that requires very clean conditions. So how do you do this?
Well, we have a clean room. We've done this in clean room.
So I don't sorry?
We have a clean room.
Ah, clean room. Okay,
yeah.
okay. That's and for the reagents, do you use any standard operation or?
Yeah.
Yeah. So we have time for questions. Yes, one over there. Yeah, thank you.
Can you hear me? Okay. Yeah. I'm Veronica Preda from University of Bucharest, and right now I'm studying molecular biology, so I'm working a lot with cells. I was interested to know whether your method has rejected specific cell lines. I mean, I have seen that you have worked on HepG2 cells, and also on hair, I think, I saw something, and there was something else, HeLa cells, if I'm not wrong, but are there any cell lines you tried and your method has rejected them, like, okay, I don't work if you give me this cell line?
Okay, yeah, at present, in most cases, we just use HepG2 cells, and also, as you can see, we also use the HeLa cells and also SCC-7 and some cells like that. But at present, I do not find the cells reject the metals at present, because normally, if you use the metal incubated with the cells, the cells will uptake the metals.
Okay,
yeah.
I understand now. I was just curious if there is any selectivity for a specific type of cell line.
Oh, no.
Okay, thank you.
Yeah.
And can we apply this also for prokaryotic cells, for bacteria, for example? Or just for eukaryotic cells?
I think it should be can. Yeah, I should can. Yeah.
Okay.
Yeah.
Thank you very much. I was impressed by the presentation.
Okay, thank you.
Congratulations.
Yeah.
I agree with you. An impressive presentation. More questions? Okay. Well, if there are no more questions, we thank Professor Wu again. Thank you.
Thank you.